Hi, my name is Julia Madeline Long. Today I will be presenting to you my research on mercury extraction from groundwater samples using modified graphene thiol materials. Access to clean drinking water is something that every single one of us as inhabitants of the planet Earth are dependent on. Whether you live in Uganda or Iceland or man on the moon, we're all bound biologically to this one little molecule that we call water. We are living in a time of great scientific advancement. We're making advances every day that just 50 years ago would have defined a decade. We're making advancements in medicine and how we tackle issues like climate change and hunger. And through these things, we're improving our quality of life exponentially every day. Now, when you get all wrapped up in this, wrapped up in all these scientific innovations and how well we understand the world around us now, sometimes easy to forget how precarious our situation is. Without access to clean drinking water, these advancements have nothing to stand on. We won't be there to reap their benefits. So it's really important that we never forget how dependent we are on water and how important it is for our life. So as you can see in the map that I have in front of you, the United States, Canada, Asia, most of their population has access to clean drinking water. Anywhere from 1 to 25% of people are drinking non-clean water. However, if you look over at the continent of Africa, you can see that a large portion of the continent does not have access to clean drinking water. Between 50 and 75% of people don't have access. And that's a really big problem, especially when you consider what types of contamination might be in that unclean water that they're drinking. Specifically for the purposes of this research, I'm looking at mercury groundwater contamination. Now, mercury is a neurotoxin. It wreaks havoc on the brain and on the nervous system, and if left untreated, it can be lethal. Mercury is also dangerous because it's environmentally persistent. It doesn't just go away, and it also can compound its effects through bioaccumulation. So, say there's a pond in the sub-Saharan region of Africa, and everybody in a certain village comes and eats fish from that pond. It's their food source. Now consider that in close proximity to that pond, there's a landfill. What do we put in landfills? We put our crap in landfills. Specifically, we put things that have contained mercury in the past. Mercury was used for thermometers, for car batteries, for television sets, and that stuff has all ended up in a landfill. The mercury doesn't just go away, it's biologically persistent. So it actually stays in that landfill and eventually can form what's known as a leachate, which subsequently leaches out of the landfill and into surrounding water sources. So back to our pond. Our fishes in the pond now have an increased concentration of mercury in their blood. And when a little fish gets eaten by a bigger fish, that effect is compounded again. And this cycle continues and continues until eventually the fish ends up on somebody's plate for consumption, and unfortunately results in an increased concentration of methylmercury in that person's blood. So the study that I'm referencing here looked at 3 different groundwater sources across the sub-Saharan region of Africa. And they found that according to limits set by the WHO, the US EPA, and the government of South Africa, in almost every single case, the concentration of mercury well exceeded the maximum limit concentration set forth by these agencies, which means that the water that these people are drinking is almost certainly toxic to them and can definitely have detrimental effects on their health. So there's a couple ways we can fix this problem. In the US, we use liquid-liquid extractions to purify our water. However, for a country like Africa, that's not really feasible. Not only is it really expensive to purchase all those solvents, but they don't have the infrastructure in place to do the upkeep and to disperse this water to everybody who might need it. They don't have the financial ability to, and they don't have the government control to institute that. So it's not really a realistic solution for them. Thus, the aim of this project is to develop a solid phase extraction approach to remove mercury from water using thiolated graphene materials. Graphene is a superior support structure. It has a high surface area of 2,630 meters squared per gram, which means it's really optimal for making sure that as many reactions at once is happening because of its extreme surface area. However, due to its nonpolar characteristics, it's not really good on its own for absorbing things out of solution, and that's where the thiol groups come in. So the chemical structure you see here on your screen, this is a thiol group. Thiol groups are organosulfur compounds with an alkyl group binded to a bisulfide. Now, based on the principles of hard-soft acid-base theory, we can predict that thiol is a soft alkali, which readily forms a stable compound with mercury 2 ions. Thus, by combining the graphene and the thiol groups, we can create a material that is able to take up the mercury from water, form a stable complex, then remove that complex, leaving just clean water behind. So this is a schema of my methodology. You start with graphene oxide after a reflux with toluene and thiol groups. You're left with this modified graphene thiol group. You introduce 20 milligrams of this sample into my mock water samples, which were just beakers filled with 50 mils of DI spiked with mercury 2+ standard. I shook to incorporate the mix for about 15 minutes. Then I filtered out the resulting substrate, which you can see here, which is just the exact same graphene thiol group as above, but you can see here that the bisulfide groups have actually knocked off their hydrogen and replaced it with the mercury 2+. So to filter that out, leaving just 50 mils of clean DI water. I analyzed this using a buck absorption analyzer. So you can see here on the left-hand side of your screen, this is the calibration curve that I generated using 7 different points of increasing concentrations of mercury prior to running these trials. Once I had my calibration curve, I went ahead and took 1 beaker filled with 50 mils of DI water spiked at 4 ppm of mercury 2+ standard. And then I took a beaker, an identical beaker containing the same spiked DI water. However, with this beaker, I introduced my materials, my thiolated graphene. When I measured the sample that did not have functionalized graphene in it, I got an absorbance of approximately 0.080. When I filtered out the solid from the second beaker and took the resulting filtrate and analyzed it, the absorbance was just 0.002. So there was almost 100% uptake of the mercury from that sample. Now I want to stress again that this is a preliminary trial. I still have a lot more trials to do. I would like to investigate how high I can go in the concentration of mercury and still see that same level of uptake. I would also like to investigate how much shaking has an effect on this result. But it's just a preliminary trial. This is some very promising research. Now, there's still research to be done. I still would like to do FTIR analysis of my materials. Over here on your left-hand side, you can see an FTIR of graphene versus graphene oxide. And over here, you can see an FTIR of the thiol groups. So I would like to do an FTIR of these materials together. I would also like to do thermal gravimetric analysis on my product, just again to ensure that there has been connection between the thiol groups and the graphene. And as I said in the previous slide, I would still like to do several more trials. Research potential here is huge. I included these 3 pictures here to kind of put this into context for you. I really think that this project has the capability of being useful in a very real way to people. What you see here are 3 different pictures of the methods currently used in the region that we're looking at, the sub-Saharan region of Africa, for water purification. The first picture here is ceramic water purification, which utilizes these ceramic bowls to filter the water through and remove contaminants. Here is a biosand filter, which is the same idea, but it uses a thin layer of gravel and a thin layer of sand to filter out the materials. And then the last picture here is membrane filtration. So when you apply a pressure, i.e. sucking on the straw, as you can see this woman doing here, it forces the water through a membrane, which thus removes most of the contaminants. Looking at these methods and looking at how they've already been instituted and are in use today in this region, I don't think it's a great leap to think that thiolated graphene might be able to be applied in this same sort of vein, whether as a biosand filter, where you don't have to use nearly as much material, or as a handheld membrane filter. I think there's a lot of potential here, and I truly think that this research is in the same vein as these filtration methods which are currently in use. Thus, I think that it would be pretty easy for these people to accept that it works, and also to integrate it into their lives. In conclusion, I would just like to bring us back to this picture here of our world map. I said in the beginning that most developed countries, Canada, United States, Asia, they have most of their population drinking clean water, but I want to stress that not everybody is. 1 to 25% of people are not drinking clean water. In the United States, I can think of several instances where we still have issues with water purification. In Flint, Michigan, they've been dealing with the lead crisis in their water for over 6 years. There was recently a flood in Florida of toxic waste reservoir of water has flooded out. So even though it's not as big of an issue in our country, it still is an issue. And I encourage everybody to remember that that clean water is not a given. Clean water is something that you have to work for and something that requires upkeep. My acknowledgements here, just before I let you guys go, I would like to thank Dr. Joshua Patterson for his guidance throughout this project. I'd like to thank Dr. Turk Abdel Fattah for helping me come up with the idea for this project. I'd like to thank David Spinazzola, the CEO of my company, Metropolitan Solutions, for allowing me to use the laboratory facilities and the atomic absorption buck AA for the purposes of this project. I would like to thank the organizers of this year's virtual Paideia conference. I'd like to thank Christopher Newport University for funding this project. And finally, I give my eternal gratitude to every single professor of MBCH for providing me with an unparalleled academic experience these past 6 years. Thank you.